So, hello everyone to be attending today's webinar, even though it's Monday Easter. So thank you all for being here. And today the presentation will be from Dr. Helena Gavilan. She's a researcher from University Complutense de Madrid. She works in the physical chemistry department in a group of nanocolloids and magnetism, and her research focused on the design, large-scale synthesis, and magnetical characterizations of magnetical nanoparticles and hetero structures for biomedical applications and evaluation their potential for magnetical hyperthermia. Thank you so much for accepting to do a webinar with us, Helena. And also, she's the WG3 leader of the nexMPI cost action. So thank you so much for being here and for accepting to present for us today. And the floor is yours.
Okay, so thank you and welcome everybody to this webinar related to the large-scale production of high-quality magnetic nanoparticles. Mostly I will be focusing on ferrite, and mostly I will be linking the material design and the synthesis method to hyperthermia and magnetic particle imaging capabilities. So the webinar structure will be the following. First, I will introduce you iron oxides and will give some fundamentals also about magnetism, just as very briefly. Then about magnetic hyperthermia and magnetic particle imaging and some performance metrics. Then I will focus on the scaling bottleneck in clinical translation and more specifically in the synthesis methodology of different kinds of nanoparticles like nanocubes and nanoflowers, because they have shown very interesting features for these two applications. So I will focus in these synthesis routes, and I will give some progress on the path to the gram scale of these routes. And I will finally give some home tech messages that we have to keep in mind related to mostly to the metal precursors that we use when scaling up our synthetic method. And I will finish with some conclusions. So just to begin with ferrite magnetic nanoparticles, they have an inverse spinel structure and they include iron 3 in their chemical formula. So you can find typical examples with this formula, so MFE2O4, where M can also contain manganese, iron, cobalt, nickel, and copper, and zinc, divalent metals, and most of them show superparamagnetic properties at sizes below or close to 20 nanometers in diameter. Here you can see the most common applied compositions in nanomedicine that are magnetite and magemite phases. So here you can see in particular the crystal structure of magnetite. You can see that there is a distribution of iron 2 and iron 3 ions. So we have the tetrahedral sites occupied by iron 3 ions, and octahedral sites occupied by an equal mixture of iron 2 and iron 3, okay? And so in a single unit cell, we would have 8 iron 3, 8 iron 2, and 8 iron 3 in the octahedral, and 32 oxygens. Okay, so in the case of magemite, it is the fully oxidized form of magnetite. This is nice because it's going to be even more stable chemically, although they are both very stable, and this is why they are so good for nanomedicine. And since it's fully oxidized, we will only have iron 3 plus, okay? So we will have tetrahedral sites occupied by iron 3 plus, then some more iron 3 plus ions in the octahedral, and we will have some balance vacancies that we see here in order to have a neutral and a stable compound, okay? So here you can see the XRD diffraction patterns. They are pretty similar, and we see that the most intense Bragg peak is the 311 peak. And the only difference is that in case of Magnemite, it is slightly shifted. So in case we have a mixture of phases, it's hard to tell whether we have a magnetite, Magnemite, or a mixture, especially if we are in the nanoscale. Okay, so basically we see that when we have this magnetic ordering of ions like this, we may have ferromagnetic or ferrimagnetic properties. In the case of ferrite, is ferrimagnetic. So for ferromagnetic, all atomic magnetic moments align parallel in the same direction, but in the case of the crystal structures that we saw, so ferrimagnetic, this occurs when we have magnetic moments in the tetrahedral and octahedral sublattices, which align antiparallel with unequal magnitudes. Okay, so this will result in a net magnetic moment that will be the rest, okay, of the two sublattices. Then the next thing that I want to just define briefly is the fact that we can have nanoparticles of different sizes. So we will pass from a superparamagnetic regime and to a ferrimagnetic regime. We all know that for within the superparamagnetic regime, we will have a behavior characterized by a single reversible curve. So this means that there is no hysteresis loop, there is no remanescence magnetization. So when the external field is reduced to zero, magnetization returns to zero. And also there is no coercivity. Okay, this occurs for very small nanoparticles when the thermal energy is strong enough to spontaneously flip the magnetic moment. What happens if we have bigger nanoparticles? We will enter in the ferrimagnetic regime. So we will have some hysteresis. Okay, so we have this curve loop, and the path taken when increasing the field is different when decreasing it. Okay, so we will have remanent field. If we remove the external field, we will have some coercivity. Okay, so we will need a reverse field in order to achieve a magnetization of zero. And in both cases, we are going to have a saturation magnetization. Okay, we will reach a plateau, a saturation peak point at high fields where all the internal magnetic moments of the nanoparticles are aligned with the external magnetic field. Okay. So here you can see the different metal ions that can form the ferrite nanoparticles, the electron configuration, the ampere electrons, and so the theoretical magnetic moment that they will have in magneton Bohr, okay, and the site preference in the spinel structure, okay. This was investigated by the pioneer studies of Louis Néel, okay, which was awarded the Nobel Prize in Physics in 1970. And thanks to him, we can really, 15 years later, we can understand how by tuning the composition of ferrites, we can tune the magnetic characteristics of the nanoparticles. Okay, so how does certain characteristics like saturation magnetization can be modified in iron oxides? It's very interesting the fact that if we change the shape, we can modify the saturation magnetization. And here, let me bring your attention to these three shapes, like the nanoflower structure, the nano-octahedra and nanocubes, because they will have like always in the range of 80-90 mu per gram. We will have like slightly higher saturation magnetization, and this will be advantageous for biomedical application. And if we consider spherical nanoparticles in different composition, we see that still for the ferrites, we are more or less in the range of 90 mu per gram, but selecting other composition different from ferrites, like metallic nanoparticles, like metallic iron or iron carbide, we can obtain a huge saturation magnetization value range above 150 umogram. This is also very interesting. But if we compare all, although these have higher saturation magnetization, and this is very interesting, they are for now rarely used in biomedical application because they are less stable chemically. And also in the case of cobalt, for instance, you will have severe toxic effects. Okay, so now let's move on and concentrate in these two phases in which we are interested, that are magnemite and magnetite. We have about 16 known forms of iron oxides and oxyhydroxide that can exist, and actually they are used in diverse applications, okay? But we focus on this for magnetic hyperthermia and MPI. And it's very important to understand the syntheses that are direct and indirect, because you will see that, for instance, in the case of the nanoflowers, you will have these precursors, and it's always very important to understand the synthesis methodology that you are applying, okay? So here we can see from the direct synthesis, we have iron 2 precursors that can oxidize, and the iron 2 and iron 3 precursors that can suffer hydrolysis and form directly magnetite, iron 3 that can be reduced, iron 0 precursor that can decompose into iron and then oxidize, and then some indirect synthesis that rely on the intermediate species like green or white rusts, lepidocrosite, hematite, goethite, akaganeite, and so on. But almost all clinical approved iron oxides, like former Ferridex or Resobist, were produced using this route, okay? The Massard coprecipitation technique, in which these precursors are hydrolyzed and condensed in the presence of a base. And this is because it is water-based and easily scaled for pharmaceutical production, okay? Of course, if we consider nanoparticles that can have like higher MPI and magnetic hyperthermia capabilities, we we rely on other synthesis routes that are more complex and slower, but give rise to monodispersity and to shape control, okay? So just for those interested in the foundations of these and fundamentals of these routes, please mind that Matijevic and Sugimoto were primarily working on aqueous water-based systems. Then Fernand Fievet moved to the non-aqueous solvents, specifically polyols, glycols, and Gerard Demasot in solvothermal and hydrothermal routes using reactors like high pressure reactors, and then more recently the thermal decomposition route that was developed mainly by Taiwan Hyeyeon. Okay. And now let's move to biomedical applications of magnetic nanoparticles. By engineering the structure and magnetic properties of magnetic nanoparticles, we can precisely tune different aspects of magnetic nanoparticles, like the power dissipation necessary for magnetic hyperthermia, as we will see, nonlinear response utilized by MPI, or proton relaxation required for MRI. Okay, so this is magnetic hyperthermia. This is MPI. This is a magnetic particle image scan of a mouse from the foundational research conducted at the Connolly Lab in UC Berkeley. And here you see an image, MRI image, with different contrast enhancement, T1 or T2. Okay, so we can employ our magnetic nanoparticles for these techniques and other, but I will mostly focus today the webinar in these two. Okay, so as you know, magnetic hyperthermia therapy is a nanoparticle mediated increase of temperature in the therapeutic range of 42 to 45 degrees and under alternating magnetic field, and this heat is exploited to kill tumoral cells. We know that it has the same effects as conventional hyperthermia, so reduces the viability of cancer cells, increases the sensitivity to thermotherapy and radiation, but it has advantages over chemotherapy or conventional hyperthermia because it's localized. We can remotely control the temperature, and we can repeat multiple treatments. And there were some clinical trials in the past decades. So we know that magnetic hyperthermia was well tolerated, conferred survival benefit, especially for those cases when combined with radiotherapy or chemotherapy, and induced an anti-tumor immune response. But the drawback is that a gram scale dose per patient is often required in magnetic hyperthermia clinical trials. So this was due to the limited heating capabilities of magnetic nanoparticles. So the German company who was in charge of these clinical trials stated that we stand on the need of new nanoparticles that reach higher levels of heating efficiency, embrace the concept of multimodal therapy, and guide magnetic hyperthermia with accurate nanoparticle quantification and tumor thermometry. That is where MPI plays a role and solves some of the problems that magnetic hyperthermia clinical trials had. So regarding the design of magnetic nanoparticles, the size, shape, surface, and composition can be tuned in order to offer combinational therapies ranging from gene therapy, immunotherapy, chemotherapy, radiotherapy, or photodynamic therapy and photothermal therapy. And also very interesting, the fact that we have emerging non-cancer applications for magnetic hyperthermia. For instance, relying on the on-demand release of drugs for therapeutic purposes, for tissue cryopreservation and rewarning, bacterial treatment, and manipulation of signals. Let me go back to the... Okay, so what is the heat dissipation mechanism? We know that when applying an alternating magnetic field for superparamagnetic nanoparticles, this hysteresis loop will be open and the thermal loss will be proportional to the area. This is related to the magnetic relaxation of the nanoparticles that can be either nil, Brownian, or hysteresis losses. But in the case of small magnetic nanoparticles, the magnetic moment must overcome an energy barrier to flip, and this barrier is directly defined by K, that is the anisotropy constant. So we will have this nil magnetic relaxation, okay? We see that it depends on the magnetic anisotropy, on the volume, and also it is very much related to the characteristics of the nanoparticles, HK, that is the anisotropy field that represents the magnetic stiffness, and that is also related to K and to the saturation magnetization. So we have to keep these two formulas in mind when trying to tune the magnetic properties of nanoparticles. Then once we apply an alternative magnetic field with a frequency F, okay, so we would have this angular frequency. The power generated, the heat generated is this, defined as in this formula, okay? And we have the out-of-phase susceptibility, okay, He prima prima, which represents the component of the magnetic response that is delayed in the quadrature with the field. Okay, this means that in order to achieve some heat dissipation, there has to be a lag between the nanoparticle and the alternating magnetic field applied. Okay, we can write this formula in terms of the equilibrium susceptibility. Okay, and we consider this term here with the effective relaxation time that, again, in case of the very small particles, we would have, it would be dominated by nil magnetic relaxation. Okay, so just as a sum up, if let's imagine that we would have a very fast relaxation time, okay, This would mean that we have a perfectly reversible system. Okay, there is no lag, so this means that no heat is going to be dissipated. Let's imagine that we have a magnetic relaxation that is very long, so infinite. This is a situation where we would have a locked spin. So this happens when we have a very hard magnetic material. There is an excessive lag, and also we would have low heat, okay, dissipated. So the sweet spot is when we have a maximized out of phase component, so optimized lag, let's say, and we would have in this under this condition, so when omega times this relaxation tends to be 1, if we consider the formula I showed you before, and we will have optimized heat released. Okay, so when we look at the different materials that I showed you, the saturation magnetization, anisotropy constant, anisotropy field, coercivity, we see that iron oxide, like magnetite, are soft and are good for magnetic hyperthermia under clinical conditions. Okay. Then, of course, we have magnetic iron. As I said, it has very high saturation magnetization, but is quite soft, and it flips too fast. So in the end, there is no lagging, and in order to have a lag, we would need very high alternating magnetic field conditions, so it wouldn't meet the clinical conditions. Then we have other materials like iron carbide that can be very interesting, and maybe it will be more developed and exploited in the future. And cobalt ferrite that is too hard. So in order to open the hysteresis loop, it would require very, let's say, bigger applied amplitudes of the alternating magnetic field. So this is why iron oxide is a good, we have a nice magnetic properties for magnetic hyperthermia. How to quantify the heat dissipated by the nanoparticles in terms of the specific absorption rate, that is the same as the specific lost power, SIR or SLP, okay? And we can do calorimetric method to determine it, or magnetometric method. In the calorimetric method, we register the temperature of the sample over time, and we can consider in the specific heat capacity of the dispersion medium and the mass of the nanoparticles, we can determine SAR. So the higher the SAR, the higher heat dissipated. Also, we have the magnetometric method, where we register the area of this hysteresis loop. In one cycle, we would multiply it by the frequency, so the number of cycles, let's say, and normalize it by the mass, and we would have also our SAR value. Then we have to mind that sometimes you will encounter the intrinsic loss power, ILP, that is the normalized SAR value considering the amplitude used and the frequency used, but this is only valid for, let's say, small particles. So there are some biological limits found in the field conditions for magnetic hyperthermia. We cannot apply the field conditions that we want because we are going to have non-specific eddy currents, so unspecific heat. Different limits have been established in literature. Like this is the one from the clinical trials from Jordan. Okay, and then we have Atkinson and Brezovich criteria and Herd criteria, but all in all, we must have the frequency in this range and appropriate field intensity of few kiloamps per meter, okay, like below 25 kiloamps per meter. The next application that we will see today is magnetic particle image, and here I will be very brief because we had other webinars about it. We know that it's a diagnostic tool, provides a quantitative background-free tracer imaging that can be combined with other modalities like computed tomography or MRI, which would add anatomical detail. Here you have an in vivo distribution study of magnetic nanoparticles in a mouse model where you can see the MPI signal coming from the nanoparticles that have accumulated in organs that are the bright white yellow areas. And this signal directly correlates with the concentration of iron. So this is why I say that it's a quantitative tool. And a magnetic field gradient is applied to produce the image, okay? To define first a zero field region. Then MPI detects the nonlinear response of the magnetic nanoparticles under the application of a sinusoidal drive magnetic field, okay? So this here we see the Langevin curve that describes how the magnetization depends on the field, independent of time. And then this is the actual signal that would be produced after the alternating magnetic field is applied in this region. So we would excite only these particles, and we see that it is different from the alternating magnetic field. So we will have some flat regions in the signal and some sharp transitions. This is the distortion that introduces the higher harmonics, okay? So basically the receiver coil measures a time domain signal. This signal processing reveals the frequency content and the amplitudes of these higher harmonics, and this is the kind of spectrum that we obtain, the harmonic spectrum. So the amplitude of these harmonics encode the particle location and concentration, okay? What do we use to evaluate the magnetic nanoparticles that are produced in the lab? We would make a final MPI signal that would be generated by the field-free region when moving while recording the time domain signal. And so we would have the map signal that is the point spread function, okay? And in magnetic particle imaging, this point spread function is the fundamental metric used to describe the system spatial resolution. Other things, the things that we can assess is the peak height, okay, that will tell us the sensitivity. But since it depends on the scanner design, normally this MPI signal is normalized, and this sensitivity will tell us can this system detect like very tiny tumors, for instance? Then also it is important the full width at half maximum of the signal that it will tell us the resolution. So can I resolve two proximal lymph nodes as distinct entities, for instance? This resolution is given in millivolts or millimeters, okay? And also, in order to assess the potential for MPI, we use MPS, magnetic particle spectroscopy, calculating the similar point spread functions and also signal to noise ratios in order to assess if the magnetic signal is clear and distinct from the background interference. So basically here we have different tracers, MPI tracers. So basically with this technique and this characterization, different nanoparticle types produce different signals intensities and image sharpness despite having the same amount of iron. So this means that it's extremely important to tune the magnetic properties and to tune the size and the shape and the composition of the nanoparticles to have optimized capabilities. Just to finish with this introduction, there's a clear benefit when combining hyperthermia with MPI because of the real-time magnetic nanoparticle quantification, the spatial location, temperature monitoring, and in order to overcome the blind heating limitation because MPI enables the adjustment of the magnetic field based on the specific nanoparticle distribution. Okay, so let's continue with the scaling bottleneck in clinical translation. So we have seen that magnetic hyperthermia had benefits in the clinical trials, and we have seen that MPI can be coupled and have a single monitorable platform for diverse oncological and non-oncological applications. So now, how then should magnetic nanoparticles development proceed to ensure successful clinical translation? We have these different steps, okay? The journey from the laboratory scale nanoparticle production to the market-ready product entails these 6 steps. And in order to make like a product, a nanomedicine formulation, we have to comply some manufacturing practices and to assess a batch-to-batch variation during the scale-up. So all in all, the control of certain physicochemical properties like the particle size, the morphology, surface properties, chemical structure and degradation, drug release are really important to be optimized during the industrial scale. Okay? So all these physicochemical properties are essential, but also the assessment of the batch-to-batch variation in terms of magnetic hyperthermia and MPI capabilities. So how from coprecipitation, that is the synthesis route that was applied to most of the commercial samples, to the thermal decomposition, that is one of the routes that have been developed and that offers best properties for the nanoparticles. What has been, let's say, how do they work? On the one hand, we have the coprecipitation, that is a hydrolytic salt gel route. The pros that it has is that it offers a low cost, high yield, so we obtain 10 to 50 grams, and particles are water dispersible. And this is why, as I said, commercial samples were produced like this. Some cons are the low control, so poor monodispersity, low crystallinity, lower saturation magnetization value, which degrades both the MPI signal and the magnetic hyperthermia heating efficiency. And on the other hand, we have the non-hydrolytic salt gel reactions, like the solvothermal or the polyol synthesis or the high temperature thermal decomposition, okay? And the pros is that we have high control of the size and shape, as I said, high crystallinity, and the cons are clear. We have lower yield, so we can produce generally up to 5 grams per batch. So this is easily 10 times less, even more, and require complex phase transfer for biological compatibility. Okay, so even so, we have some samples that are commercial, so far limited to specialized R&D, like SuperSpy or Sinomag. But it's basically like this. We have some salts or coordination complexes that will decompose, okay, in the presence of the solvent and in the presence of certain ligands, okay. In the case of high temperature thermal decomposition, we will have organic high boiling point solvents like octadecene or olailamine. In the case of solvothermal or polyol, we will have ethylene glycol, diethylene glycol, or for solvothermal, we can have some primary alcohols or diols as well. So now I'm going to focus on on 2 examples of magnetic nanoparticles that have very interesting features for MPI and magnetic hyperthermia, that are nanocubes and nanoflowers. Why do they have a nice magnetic feature? What nice magnetic features do they offer? They have high saturation magnetization, high crystallinity, and in the case of the cubic, low surface spin disorder, given the shape. And in the case of the nanoflowers, this would be a nanoflower. You see different petals composing the overall nanoflower, you have likewise high saturation magnetization, high crystallinity, and you have exchange interaction between the petals. So this is why you have very nice magnetic properties and improved SAR values. So first, let's start with the nanocubes. Normally, nanocubes are produced by a thermal decomposition route, okay? Normally, dibenzyl ether is employed with some surfactant like decanoic acid, okay? You obtain these monodisperse nanocubes. You have this temperature ramp. First you degassed, then you nucleate the nanoparticles, and on a third step, you grow these nanocubes. Okay, so you separate the nucleation and the growth, and this helps with the monodispersity of the sample. The first limitation of this route is that normally milligrams are produced. Let's say in the best case scenario, 30 milligrams. And then you have some limitation related to the refluxing, okay? So there are some thermal instabilities because the benzyl ether doesn't really allow you to achieve those high temperatures, and it will, let's say, decompose. And this is why normally you add additional solvents like squalene in order to achieve, let's say, a more stable temperature, okay? So another interesting point of this route, thermal decomposition, is that instead of the using one single metal precursor like iron acetylacetonate, you can mix it and add different metal precursors that allow you to tune the nanoparticle composition. For instance, in this work, we used cobalt acetylacetonate, zinc acetylacetonate, or both. So iron acetylacetonate and then zinc and cobalt acetylacetonates. Okay, we were able to produce very nice nanocubes. Okay, ranging from iron oxide to zinc ferrite composition, cobalt ferrite composition, or a mixture of cobalt and zinc. Then we studied the heating and registered the hysteresis loop under the hyperthermia conditions, alternating magnetic fields of 100 kilohertz and 24 kiloamps per meter, under increasing percentage of glycerol. Glycerol is highly viscous, and what we found is that cobalt ferrite nanoparticles close very rapidly when increasing the glycerol content, well, even initially, the loop, okay? And iron oxide and zinc ferrite had still a open, nice and open hysteresis loop, and this is why you have a much more stable SAR for higher viscosity values, okay? In the case of zinc and cobalt, you still, since you have some cobalt, the hysteresis loop is nearly closed, okay? And this is what you see for in this graph with the SAR values for different viscosity parameters. We see that even at the beginning, cobalt nanoparticles could hit much more, but those offering a stable value, let's say, are iron oxide, but mostly the best one was zinc ferrite. This is very nice because we saw that zinc ferrite were found to be biocompatible. Okay, in terms of MPI, we studied the performance with MPS, and we found that comparing the particles with vivo tracks, we found that iron oxide and zinc ferrite offer the best signal, okay? So this is interesting because zinc ferrite could be implemented in the future for magnetic hyperthermia and MPI to move forward in these fields, okay? Also, we studied the signal to noise ratio, and again, we found that iron oxide and zinc ferrite offer the best response. And the next thing that I wanted to draw your attention in is that these instabilities that I said that it is related to the fact that the ventilator decomposes is because at high temperature, the thermolysis releases certain molecules, toluene, benzaldehyde, and benzyl alcohol, okay, which have much lower boiling points, okay? This is why we see these jumps in the temperature. So in order to try to scale up and make this route, let's say, improved, we took benzaldehyde, one of the decomposition byproducts of the benzyl okay? And we assessed the size and shape regulating properties. So basically we took it and we use it in a solvothermal approach, okay? To scale up the synthesis of the nanocubes. Remember that we obtain in the range of milligrams for thermal decomposition. So in this case, you can, I optimized a solvothermal route with an alcoholic solvent, fatty acid like oleic acid, and a fatty amine like hexadecylamine. The solvent frequently was octanol. We use iron pentacarbonyl, so not iron acetylacetonate. And we use benzaldehyde. So if you don't use benzaldehyde, you obtain particles like this, so really not cubic and aggregated, and also without a clear shape. But in the case, so why did we use octanol? Because it could dissolve ligands of different nature, like the benzaldehyde that I told you. Also, the boiling point is lower temperature, so we will have an improvement in the energy consumption. And we used high pressure vessels, like these autoclaves here, because we achieve high pressure conditions, so we achieve high crystallinity, and we can parallelize easily the synthesis, okay? So this was the route that I came up with using a aromatic or aliphatic aldehyde. So I will tell you the results. The difference is clear, right? When using benzaldehyde, we obtain really monodisperse iron oxide nanocubes. This is the size distribution, really crystalline, okay? We also saw the combination of benzyl alcohol that didn't really lead to nanocubes, but only the combination with benzaldehyde led to the formation of nanocubes. So really this ligand that was unexplored is pretty much related to the cubic shape, okay? Benzaldehyde was not the only aromatic aldehyde that works in producing nanocubes, but there are other examples, okay, that you can use. And while meta and para substitution of the aromatic ring is fine and works in some ways, ortho substitution doesn't work. So you have to take this into account when scaling up your solvothermal route. So benzaldehyde was used to study key experimental parameters to control the size of the nanocubes, okay? We studied the autoclave filling percentage, the crystallization time in the oven, and the oven temperature, okay? And we were able to produce nanocubes in this size range, so from 5 to nearly 40 nanometers, and we could exchange the surface from oleic acid to tetramethylammonium hydroxide. This is a quite straightforward and easy way to solubilize the particles in water. And we saw that the SAR properties were really the same as those obtained with thermal decomposition, and we found an optimal size of optimal heating for 18 nanometers, okay? you can see the saturation magnetization values are very high and close to the bulk value, just like with thermal decomposition. So this is very interesting because we were able to produce much more material and at lower temperatures, and the nanocubes had the same potential for magnetic hyperthermia, okay? Also very interesting when trying to use other kind of aldehydes like aliphatic, so no aromatic ring, you completely lose the cubic shape and you have nice spherical particles, okay? If you alter the aldehyde structure, okay, and you keep adding like carbons in between the aldehyde group and the aromatic ring, you progressively lose the cubic shape and you have this hexagonal shape that also have interesting heating capabilities for sure. And also, if you combine benzaldehyde and replace the fatty amine with a secondary or tertiary amine, okay, or with an unsaturated amine like oleilamine, frequently used in thermal decomposition, what you get is nanostars, okay? And these nanostars had a better performance in comparison with the nanocubes, okay? So this means that by employing an alcohol and a aldehyde, you can really tune the size and the shape of the particles, okay? This route is also compatible with the tuning, so we could produce zinc ferrite nanoparticles and manganese ferrite nanoparticles. Okay, this is a comparison of the SAR values that we got. And in the case of the zinc is something that I don't really understand because it's a bit in contradiction to the previous paper, but we didn't see a clear difference, okay, in terms of the SAR. And in the case of manganese ferrite, there was a slight improvement in the SAR values. Okay, so also in all cases, the particles were highly crystalline, but the important thing here is that in contrast to thermal decomposition that you normally use a 2:1 molar ratio between the metal precursors, in this case you have to use very high molar ratios of 28 to 1, okay? So you use really a tiny or amount of metal precursor. So you use a mixture of iron pentacarbonyl and the metal acetylacetoate, okay? In terms of the mass produced per batch, we did parallelized reactions in the oven, simply introducing multiple autoclaves, okay? And we could obtain 4 grams of particles per cycle, okay? The iron conversion is really low, so 9 to 13%. This means that in this route is very promising, but still there's plenty to optimize. And some parameters that we work with were temperature in the oven and the autoclave filling percentage. Okay, so in the end, we managed to get 4.4 grams per cycle, okay? And by increasing the temperature, we could increase the iron conversion to 25 to 35%. Okay, so it's much better, but still is low. So there is plenty to still optimize for this solvothermal route. Also, it's compatible with the use of bigger reactors like PAR reactor, okay, so pressurized reactor. And by using a pressurized reactor, we could even increase the mass obtained per batch, okay, when considering an autoclave of the similar volume. So in the end, we managed to produce very similar nanocubes, okay, with very high SAR values, okay, employing this reactor. In the end, our best result was an iron conversion over 70% with an optimal volume of 18 nanometers. So we consider that this is the optimal size. Let me also clarify that by thermal decomposition, so far I have mentioned iron acetylacetonate, but there are other precursors that you can use, like iron olate. Okay, iron olate is commercial, but normally the chemist will produce it in the lab. Okay, so you first synthesize the iron olate and then you decompose it. Okay, so this is a very, let's say, a stable precursor. And you can, when using sodium olate in the synthesis and a mixture of organic high boiling point solvents, you can get nice nanocubes. The only problem is that with iron olate, you get this shell. I don't know if you can notice this, but instead of getting magnetite, you will end up with a mixture of phases. So you would produce a mixture of magnetite and wüstite. Wüstite is an antiferromagnetic phase. It's not nice for magnetic hyperthermia or magnetic particle imaging. So you need an extra phase in which you anneal it. So you heat it up and it oxidizes to magnetite, okay? And then in the literature, you can find even the decomposition of coetite, okay? Thermal decomposition. Here you can only see like faceted nanoparticles. They are not cubic. I couldn't find any examples of cubic nanoparticles employing goethite as an starting metal precursor. But it's very interesting because this precursor is very stable, easy to get, cheap. So it's very interesting, the fact that we can employ it in a thermal decomposition to get faceted nanoparticles, okay? The next example that I wanted you to show in this webinar are magnetic nanoflowers. Magnetic nanoflowers were produced in the past year by a polyol method. So in this case, we don't have a organic high boiling point solvent. We don't have let's say, octanol. We have a polyol like diethylene glycol. And it's very interesting because here you use a mixture of iron chloride 2 and 3, okay? So a mixture of metal precursors. And we use N-methyl diethanolamine. This is a organic amine, okay? That provides a very viscous media. And when combined, you heat them for a very long time. And the authors afterwards made electrostatic fractionation just to have more monodisperse samples, let's say. And this has been, up to now, one of the gold standards for magnetic hyperthermia and MPI. Actually, Sinomac sample is this one, so iron oxide nanoflowers. And you can see in terms of MPI quality factor, they are the one performing best. And also in case of the SLP, so the heating properties with these conditions of the alternating magnetic field, Sinomac samples are the one performing better. Okay, so I think this is a very nice nanoparticle system. And also it was found that this protocol that normally takes place under reflux for very long periods of time could be optimized by using Teflon line stainless steel autoclaves, just like I showed for the solvothermal route for the nanocubes. And this is very advisable when scaling up a technology because you solve problems related with reflux conditions and in terms of differences in the temperature, okay? So you will have more thermal gradients that hinder scalability, okay? So the synthesis of the nanoflowers was demonstrated for this kind of in this kind of reactor. Okay, so we have nanoflowers that are pretty similar, like those obtained under reflux conditions. You can tune the synthesis time in order to tune the structure of the nanoflowers. And here is very important the use of the amine, the NMDA, okay? Because it's not only a co-solvent, but also it has some important coordination properties. Okay, it acts as a high donor ligand that forms strong coordination complexes with iron 2 and iron 3. And this interaction is essential for controlling the nucleation and growth processes, okay? So based on the amount or the concentration of this amine, we will pass from a classical crystallization pathway in which single core crystals will grow to a non-classical crystallization pathway in which we stabilize the precursor, that is a green rust-like precursor. We have a slow nucleation because I told you that this it has some coordination properties and it's really viscous, so it will slow nucleation and will lead to the oriented attachment growth. And so we will end up with these nice petals that are aligned and provides a crystalline and monocrystalline. Okay, of course, if you keep on heating this system, in the end, you would obtain a large nanocrystal, okay? So keep in mind that the use of this amine is crucial in obtaining the nanoflowers and that it regulates the crystallization process, okay? So if we want to obtain a non-classical crystallization pathway, you use this amine. The next system that I wanted to tell you about is the iron oxide Rubik cube nanoparticles. So it's basically a combination of a nanoflower or a multicore particle in a cube, okay? When starting from the solvothermal route that I showed you, in which you use octanol, oleic acid, the fatty amine, and the benzaldehyde, for instance, or other aromatic aldehyde that were found to determine the cubic shape, you can use other other ligands that were not studied before that are ketones. Okay, so ketones, when combined with aldehydes, can really change the internal structure of the particle that you obtain, and you would end up with this Rubik-like multicore nanoparticle, but the overall shape of the particles is like cubic, okay? So this happens because the ketone reacts with the fatty amine, okay? So there's a primary reaction occurring that is facilitated with the oleic acid, so by the surfactant at high temperature, okay? So you will have a self-polymerization of this ketone that in the end will be a conjugated species that can interact and adhere to the surface of the forming nanoparticles and favor the crystal growth along specific lattice directions, forming the final multicore shaped structures or Rubik cube nanoparticles. Okay, so basically we are combining the nice features of the nanoflowers and the nice features of the cubic particles. These are the SAR values of these Rubik-like nanoparticles. Okay, so here we obtained Rubik-like particles from 19 to 42 nanometers, and we can see really high values of the SAR. Okay, with mild, let's say, with let's say frequencies that are acceptable for the biomedical applications. And also we can see that in comparison with Vivotrax, these particles had a more intense MPS signal, much more intense, especially those of 27 and 42, okay? So you can see that the signal is more intense and the width is reduced. So we pass from 13 to 8, okay? And also we could see the MPI signal that again, especially that of 27 nanometers, has a better signal than Vivotrax. Okay, here you can see how the contrast is enhanced. Okay, so you see that how the relaxation of the particles measured by MPS changes over the days. So we measure during 110 days. Okay, so the particles, the 27 one that in the end were found to be the best ones, were really, really stable. And how it changes the MPS signal normalize, how it changes when dispersing the particles in viscous media, in glycerol. Okay, so we see that there is a decrease, which when studied in 11 days. Okay, so there and we could see a change. Okay. Very interesting, in the case of the 27 Rubik-like particles, we studied the SAR also in 110 kilohertz and 200 kilohertz, 250 and 300 kilohertz when dispersed in water or in 50% glycerol, so high concentration of glycerol, very viscous. And we could have really high values even when dispersed in glycerol. Okay, so this is a new and very interesting magnetic particle system that again, since we are doing it in a solvothermal and in an autoclave, it can be easily parallelized and we can scale it up. Okay, so also for this case, we could scale up the synthesis up to 5 grams. Also, another important point is that the reproducibility of this method could be improved if solution 1, so the octanol, the oleic acid, and the hexadecylamine was mixed with the ketone, okay, preheated in advance for 2 hours, and then used for the synthesis in a second step. And I think this is a very important point for in order to scale up methods and in order to obtain monodisperse nanoparticles, because and the aging of stock solutions, sometimes it can be better in order to obtain a more robust method. So just some home-taking message that I wanted to tell you related to the metal precursor, because this is a key reagent when scaling up a synthesis method. We have seen iron chloride 3 and iron chloride 2, goethite, iron oolate, we have seen iron acetylacetonate, and we have seen the one used in the solvothermal, so iron pentacarbonyl. We have to mind the price and the availability of these precursors, okay? Because iron chlorides are super cheap and highly available, but iron pentacarbonyl is not. The price is high, and there are some regulations because it's volatile, because it has toxicity. So this also must to be taken into account when scaling up any methodology. Okay. Also, the composition temperature. Okay. In case of iron pentacarbonyl, it is true that this is lower, and this is why it's still being used. It's very convenient. And also, if we use lower temperatures, we save energy. So there has to be like a balance. And then there's iron chloride 2 and 3 or goethite, that since they rely on hydrolysis and phase transformation for goethite, then it's another story, okay? But EU demands the use of metal precursors that are stable and lower toxicity, and scale-up production should be optimized in parallel to be efficient in terms of energy and the costs. Then also, it's important to mind that the composition of iron pentacarbonyl is really clean and sudden. So we lost in a very easy way identical CO ligands, okay? But in the case of the acetylacetonate and the iron olate, we have a chelated or ionic coordination. So it's much more difficult. This is why the composition temperatures are higher, okay? And the one of the acetylacetonate is radical driven, so it relies on the breakdown of the acetylacetonate ring. And in the case of the iron olate, it's a multi-step dissociation of the long chain of the fatty acids. So this tells us that there is plenty of room to improve these methodologies, okay? And if we could use goethite when there is no decomposition and there's just lattice dehydration or iron chloride 2 or 3, it would be more advisable, let's say. So I wanted just to mention that for the large-scale production of high-quality magnetic nanoparticles, so designed for magnetic hyperthermia and MPI, employing metal precursors that are safe and that are associated to energy-efficient methods is a challenge and will aid the development of clinical compatible nanopharmaceuticals. And I just want to conclude this webinar by telling that regarding to the magnetic nanoparticles, tuning the anisotropy and the anisotropy field leads to an improvement in hyperthermia and MPI imaging capabilities. Considering the cubic iron oxide like magnetite and magamites, doping with zinc is very interesting. It is a safe way to keep hyperthermia and MPI imaging capabilities in viscous media. Then for Rubik cube iron oxide nanoparticles, this new system is very interesting because it has high hyperthermia and MPI imaging capabilities even in viscous media. And then for solvothermal and polyol methods, typically carried out in autoclave reactors, this helps scaling up the mass produced per batch and controlling the temperature of the process. Of course, with co-precipitation, you obtain 10 times more, but it is an important step ahead the production, scale-up production of high-quality nanoparticles, the solvothermal and the polyol methods. And then it is interesting the use of shape-directing agents like aldehydes and ketones that determine the size and the shape when scaling up the synthetic processes. And also it's important the reproducibility when working with a stock solution for certain reactants. Okay, finally, I just want to say that scaling these methods for higher efficiency and safety is essential to meet EU good manufacturing practice standards, which require rigorous batch-to-batch reproducibility and the elimination of toxic precursors to ensure patient safety and regulatory approval for clinical use. So with this, I would like to conclude. If you want additional resources regarding MPI fundamentals or system physics or MPI tracers development with respect to the polymer coating or transfer to aqueous media, all these resources they are available in nexMPI website. So thank you for listening, and if you have any question, I'll be happy to answer.
Okay, thank you once again, Helena, for your presentation. Yes, we have, I think we have time for one or two questions. If people from the chat would like to, okay, I think we already have one question so far. Okay, it's from João Costa. Good afternoon. Thank you for sharing your interesting work, of course. Thank you, Helena, again. João has a question related to when you measure the MPI signal to a iron oxide magnetic nanoparticle, do you measure them in colloidal stability of the magnetic nanoparticle solution, or okay, I'm just having some problems, or have you already tried to measure the signals of the magnetic nanoparticle stability stabilized in any kind of cells culture or alpha mem solution or any different kind of solution?
So
In
I
any
didn't
case,
have,
okay, so
you mean whether this was assessed in biological media?
yes, it seems so. Like in the case you already tried to stabilize the magnetic nanoparticles in cells culture, with coating you used to stabilize them if you did so.
Yes, yes. I didn't have time to speak about the coating, but mostly we use gallol PEG. So in principle, for iron oxide, catechol group works really nice because it has multiple oxygen that can really bind and will have high affinity towards iron on the surface of the nanoparticles. And catechol group coated coupled with polyethylene glycol has allowed us like the best stability in complex media, let's say. So the ligand that I showed, tetramethylammonium hydroxide, is nice just for magnetic characterization, like initially, but for this kind of advanced studies, we go for bigger, more efficient coatings.
Well done. We understood. Did that answer your question, João? Okay, he didn't answer yet. Okay, so I think we have enough time for a second question from yeah, he said yes, thank you. So we have a second question, and from Caio Santos, and his question is: how does the choice of precursors influence the colloidal stability of these systems, and to what extent is colloidal stability critical for obtaining a high quality images in MPI or having magnetical hyperthermia application, a high potential for the magnetical hyperthermia. I think so.
Is really really interesting to have is really really important to have initial stability of your particles, as synthesized nanoparticles must be stable. If not, then afterwards, when transferring to aqueous media, is going to, or for MPI or magnetic hyperthermia characterization, you will not exploit, I don't know, the shape that you have exploited or the size that you have achieved. So you will have a cluster of nanoparticles. So it is, of course, essential to add some molecules that will control the size and that will coat the nanoparticles during the synthesis. This is why in thermal decomposition you add oleic acid or decanoic acid. In the case of the solvothermal as well, you add the oleic acid. You can add other, of course. So, but yes, I believe it is really, really important to add, besides the shape directing agent, something that will bind the surface of your nanoparticle during the synthesis.
Okay, great. I think we just have enough time for the last question from Arda. And just to remind you that this presentation is being recorded, and we're going to post this webinar in our YouTube page. So if you don't have the link, just ask. We can share there. And Arda question is, like to ask if there is the temperature dependency of magnetization graphs that you can show the graphs, or temperature dependence of the magnetic susceptibility graphs one more time, please. But well, you can have. I think these graphs were in the presentation, right?
What a graph again? Tell me.
The dependency of magnetization, or the temperature dependency of the magnetic susceptibility. But you can go to the presentation when we post it as well, Arda.
So at the beginning, right?
Yes, in the beginning.
Let me see, because I am not so sure on about which slide are you talking about. So which one is it again?
The question is Adam missed the beginning of the presentation and would like to know if there was this information related to the temperature dependency of the magnetization graphic.
I didn't add it because there's another webinar about fundamentals of nanomagnetism. So you want to know like the dependency of the Curie temperature or?
Yes, that's the answer.
Yes, I didn't add this information because, as I said, there is one specific webinar about the fundamentals of nanomagnetism. This was more about how you can tune the magnetic properties by tuning the composition. But what you should expect is that you have a Curie temperature and the magnetization will drop above this Curie temperature.
So
Is this?
Ada, you can go to the website, our YouTube page or our the nexMPI website and
Yes.
search for this video, and we have already posted there. Okay.
Yeah,
I
yeah,
don't
I
remember
recommend.
who give the lecture, but yes, we have it there. Okay.
Okay.
So Helena, once again, congratulations for your presentation. We have a lot of possibilities when it comes to obtain a high quality magnetic nanoparticles for different applications. So thank you all for being here, for the audience, and see you in a month for the May webinar. And thank you, Helena, and stay
No, thanks
tuned.
to you, and I am sorry because I was a bit long,
Don't worry, don't worry. There is a lot of content to be
but
shared, so we
it is my
understand.
passion, the synthesis of nanoparticles.
It was great. So thank you all. See you soon and stay tuned that we have news from the next days. Okay?
Okay, thank you. Bye bye.
Bye bye.